So how do the image and the kernel sort of fit into the picture of a linear transformation and what a linear transformation is doing? So I'm going to try and just write up a sketch here that does some justice to the idea. So if I have a linear transformation like the one that we just looked at, this was a linear transformation from, it was three-dimensional space into four-dimensional space. And so the picture that I have in my mind is that I've got a three-dimensional vector space, so it looks like x, y, z space over here. That's my domain. And then the codomain of my linear transformation is some four-dimensional vector space. And what does a four-dimensional vector space look like? I don't know. It kind of looks like three-dimensional space with an extra dimension. I don't know. It's not a very satisfying way to draw it, because drawing four-dimensional space on a two-dimensional whiteboard is losing a lot of information. It's losing two whole dimensions of information. And so the kernel of the transformation that transforms a four-dimensional space onto a two-dimensional whiteboard is a two-dimensional kernel. We lose two dimensions of information. Anyway, so if this is my linear transformation from R3 into R4, then what's going on with respect to the particular example that we just looked at? So we just looked at this example where the basis for the kernel, the null space, is the vector 3, 1, 0. So another way to think about that is that that vector as a vector in my domain over here, 3, 1, 0, so maybe it looks like this. So it's in the xy plane, maybe somewhere here. Right? So this is 3, 1, 0 as a vector in the xy plane. And so the span of that vector, well, that's going to be, in this example at least, a whole line's worth of points, all of which lie in the xy plane. That line is what we would call the kernel of my linear transformation. And the reason it's called the kernel is what the linear transformation does to it. What the linear transformation does to it is it sends every single point from that line, every single point along that span, gets sent to the zero vector in the codomain. So it's almost like it's squashing. It's taking that whole line that is going in this direction and just smushing it away, right? And when I smush it away, it all becomes the zero vector in my four-dimensional context. Meanwhile, there's a whole bunch of stuff back in my two-dimensional plane over here that's not getting squished, right? In fact, one of the ways to think about what's not getting squished is it's kind of the two leftover dimensions are what's not getting squished. So I might sort of look at it like this, that I have these other two dimensions here, and if you like, we could make this perpendicular to my kernel. My other two dimensions, these are the two dimensions that don't get squished by my transformation. And so what my transformation is doing is it's taking those two dimensions that aren't getting squished, and it's just sort of spiriting them over and setting them inside of my four-dimensional space in some way. Right? So the image of this linear transformation is where we're setting down this plane, in this example, a plane of two-dimensional space that's not getting squished away. And so that then becomes my image. So maybe over here, I got a plane that looks something like this. And this plane is then what I would call the image of T. It resides in the codomain, right? And it has the property that the linear transformation, if I have a basis for my image over here, so here is a basis for my image, and in the example that we just did a minute ago, a basis was, for example, I'm going to call these vectors v1 and v2. v1 was 1, 2, 0, negative 1. v2. So notice that these are four-dimensional vectors, right? They're vectors in four-dimensional space because that's where my image resides. It resides in the codomain of my transformation. And so these vectors, they're columns of my original matrix, and so they represent vectors in the codomain. And collectively, these two vectors span the entirety of the image of my linear transformation. And my linear transformation from this orange space back here, which we didn't give a name to, but I'm going to do it anyway, just because. We call this the row space of my linear transformation. So what the linear transformation T actually does is it takes the row space of T, which is everything that's not getting squished in my domain, and it just places a carbon copy of it in some orientation as a subspace of the codomain that's called the column space. And so what we can say is every linear transformation is a one-to-one and onto transformation from row space to column space. So the row space and the column space always have the same number of dimensions. In this case, my image was two-dimensional, and so was my row space. And that's not a coincidence. In fact, that's the last thing that we're sort of asked to reflect upon in this chapter, is the relationship between the image and the kernel, the dimensions of the image and the kernel of our matrix. So one of the really sort of striking features of this, right, is that the column space, the image, was the span of the columns of my matrix. So if I want to know what my image of my linear transformation is, it's just the span of all the columns. Meanwhile, the row space back here is called the row space because it's actually the span of the rows. Each row of my original matrix is perpendicular to the kernel of my matrix. And you can convince yourself about why that is just by looking at an example, right? If I take a row of one of my matrices and I take a vector which belongs to the kernel, then the dot product of that row with that vector must be 0, because in the product, in the matrix vector product that gives me the homogeneous equation, we get exactly the dot product of the rows of the matrix with the column vector that we're supplying. So yeah, in this example, our kernel is a line in three-dimensional space.
Yep.
And the row space is a plane in three-dimensional space, and the relationship that they have to one another is that they are perpendicular to one another, right?
Thank you.
It makes a right angle
Yep.
with the, yeah. So another way to say this is that the kernel, in this case, a basis for the kernel is actually a normal vector to the plane, which is the row space of this particular matrix.
Okay. Yeah,
So,
the way the line was kind of drawn with the plane.
Yeah, right. It's hard. Again,
Yeah.
three-dimensional picture on a two-dimensional whiteboard is a lot harder to do. But yeah. So the kernel is the orthogonal complement of the row space, and vice versa. So they're perpendicular to one another. And so, in particular, what that tells me. Well, let's go back to how the book is asking us to reflect it. Well, no. Let's look at the picture first, and then we'll look at how the book is asking us to think about it. So how many dimensions? Like, what would the dimension of my kernel be in this example?
One dimension?
It's one-dimensional. It's a line. The basis that you found for the kernel of T had a single vector in it. And so if we think back to what that should actually have come from, which is equal to the dimension of the kernel of T, well, the reason that there was a one-dimensional kernel is that there was one free variable in my standard matrix after we did the row reduction. In other words, there was one non-pivot column in my original matrix. So the non-pivot columns are telling me the dimension of the kernel of my transformation. So in this example, there was one non-pivot column, so one free variable, so the homogeneous equation had a one-dimensional solution space because here was its basis, right? We factor out the one free parameter to get that. So the dimension of the kernel is 1. What was the dimension of the image in this example?
2.
It was 2. And if we think about this the way that our book wants us to think about it, how would we have known what the dimension of the image was? Well, we got the image by taking the pivot columns of my original matrix. And so those were the columns that had the pivots in them instead of the columns that did not have the pivots in them. So the dimension of the image of my transformation is controlled by the number of pivot columns. So if the number of pivot columns tells me the dimension of the image, and the number of non-pivot columns tells me the dimension of the kernel, what relationship ought to exist between the dimension of the image and the dimension of the kernel? Every column is either going to be a pivot column or a non-pivot column. Those pivot columns are going to correspond to the dimensions of the image of my transformation, and the non-pivot columns are going to correspond to the dimensions of the kernel of my transformation. So when I add those two things together, what I should get is I should get the total number of columns in my original matrix. Right? That's one way to think about it. Every column is either a pivot or not a pivot, and so if I add up the pivot columns and the non-pivot columns, I get the total number of columns. But the total number of columns is, as you just said, exactly the dimension of my domain. Right? So the dimension of whatever vector space is the domain of my linear transformation. And so that's a pretty big deal. It's a big enough deal that it gets a name. It's called the Rank-Nullity Theorem. So just for kicks, we'll sort of write that down. The Rank-Nullity Theorem. So rank is nothing more than a fancy word for the dimension of the image. So when we say rank, that's what we mean. So the rank is the dimension of the image. The nullity, as the name might suggest, is the dimension of the kernel. So in this example, that's 1. And so the rank nullity theorem just says that rank plus nullity is equal to the dimension of the domain. In other words, the number of columns of my standard matrix. So here we had a one-dimensional kernel, we had a two-dimensional image, and when I add 1 plus 2, I get 3, which was the dimension of my domain space for this linear transformation. And part of that, too, is it encodes this idea that the row space actually has the same dimension as the column space. Because if we count the dimensions back here in the domain, we're really adding together the dimension of the kernel, which is 1, with the dimension of the row space, which has the same dimension as the column space. And so another thing that we get out of this for free is that the dimension of the row space is the same thing as the dimension of the column space. And that's not an obvious fact, that every matrix has exactly as many linearly independent columns as it has linearly independent rows. So remember that process that we've been using to find a linearly independent spanning set for the columns of a matrix? That same process can actually find for us a linearly independent spanning set for the rows of the matrix, because all we're doing is we're looking for the pivots. We either take the pivot columns if we're looking for a spanning set for the span of the columns, a linearly independent spanning set, a basis for the span of the columns, or we take the pivot rows if we're looking for a basis for the span of the rows. So if we look at the kernel of this linear transformation, it had a basis of 3, 1, 0. And so 3, 1, 0. And so if I look at the span of that vector 3, 1, 0, that would be the kernel of my linear transformation. So all of the points along this line would be being sent to 0 by my linear transformation. But then meanwhile, I have the rows of my matrix, and let me write all of those in here. So row 1 is the row 1, negative 3, 2. Row 2 is 2, negative 6, 0. Row 3 is 0, 0, 1. Oops. 0, 0, 1. And row 4 is negative 1, 3, 1. So I'm going to hide my kernel here for a second so that we can focus on, here are the 4 vectors that are the rows of my matrix. And when we look at them, what do you notice about these 4 vectors?
They all lie on the same plane.
They all look like they are coplanar. Yeah, they all reside in a common plane with one another. And so sure enough, if we were to take the set of all linear combinations of these vectors, just sort of write that a1 times the first row plus a2 times the second row plus a3 times the third row plus a4 times the fourth row. Oh, I guess it doesn't know how to do parameters like that. But you get the idea, yeah, that we end up with this. We end up only being able to get things that are within that plane. Let me think, what would be a good equation for that plane? How about 3x plus y is equal to 0? There we go. So there's an equation for that plane that all of my rows reside in. Right? And so if I put my kernel back into context, there's my kernel. And it happens to be perpendicular to the plane that contains all of my rows. So this blue shaded plane here is the row space of this matrix. It's the span of all 4 of these rows, which happens only to be 2-dimensional, interestingly enough. And then the kernel is this perpendicular line. So it's the line through the origin, which is perpendicular to my row space.